Okay, here we go. Polynomial and rational inequalities. And so we are not going to peek at that graph behind the pink screen until we're done. We're going to solve this inequality. And the first thing that we realize is that, wow, how? Right? Think about how we would start. And so when something looks as confusing as this, we're going to break it down in something manageable. Could we solve this if we looked at, let me get this, if we looked at x squared plus 4x plus 4 equal to 9, we could, this is manageable, right? So we're going to start someplace that's manageable. We're going to go ahead and subtract 9 from both sides. We get x squared plus 4x minus 5 equals 0. We realize we can factor that. And set each thing equal to 0. So what have we done? We have solved part of this problem, right? Because, well, let's finish this, and then we've solved part of this problem. We've solved part of the problem because it says, when is this side equal to, all right, it really says greater than or equal to, but we solved this side of when is this side equal to 9? Well, that happens when x is equal to -5 and x is equal to 1. So we've solved part of the problem, but how are we going to find out where this side of the problem is greater than 9? Well, believe it or not, we're going to use a number line to help us. And so we're going to go ahead and quickly sketch a number line. We're going to put that -5 there and put that 1 there, and we're going to remind ourselves that those are part of our solution, right? If we took the time to plug -5 in, we'd see that that equals 9, and if we plugged 1 in, that would also equal 9. And so we're going to include those by filling in circles, right? And now what we're going to do is we know that there are more answers that could make our original inequality work. And so what we're going to do is test all the intervals on either side of the two answers that we have here, -5 and 1. So we're going to test the left side of -5. And what do you think would be a good number to test? We could test, I'm going to pick -6, all right? We could test any number on the left side. I'm going to pick -6. And that means what I'm doing is I'm going back to this right here. And I am going to plug in -6 when I see x. So I have -6 squared plus 4 times -6 plus 4. I pick up the calculator, or I do it in my head, and I get 16. And I ask myself, is 16 greater than or equal to 9? I'm like, yes. Well, guess what? Welcome to the solution, the left side of -5. Now I'm going to test in between -5 and 1. What's the best number ever to test? You got it, 0. If I took the time to plug in 0 for x, I easily can see that I'm going to get 4. Is 4 greater than or equal to 9? No, it's not part of our solution, so I'm not going to shade it in. Let's test this final portion. We can pick a number that's bigger than 1, and why not pick 2? To make this video shorter, I went ahead and already plugged things in to compare so that this wasn't going to be 3 hours long. And so if you'd like to pause each time and plug in these numbers into the function using a calculator or your head, that's great, but I already did it. And yes, 16 is greater than or equal to 9. Yay. Welcome to part of the solution. But you know that we can't write a solution as a number line. We've got to look at the number line and decide to let's see, we need some good color. We need to decide to write in interval form. So I look at this part of the solution. I write that as -infinity all the way to -5. Do I include -5? Absolutely, I include it because it's a filled-in circle. And then this part of the solution, so x can be either in this interval or it can be in this interval from 1 to infinity. So my solution for an inequality is going to involve writing an interval. So now, what was this about? Don't click until we're done. So let's go ahead and look at what we've got. No peeking till we're done. Let's look at what's behind here. Well, what you see is I took the time on Desmos to put this in. So I'm really looking at x squared plus 4x plus 4. That's the graph that you see here. And I'm wondering, where is it greater than or equal to 9? Well, let's see. Here's 9 right here. So we want to see, this is how tall. We're interested in knowing when it's at least 9 or taller. So at what x's does that happen? So we're looking, it happens from when x is -5 or lower or less than, right? So let's see if I can get both things in at the same time. Look at that. That's what this interval is describing. And it's also taller than, it's either 9 or taller when x is equal to 1 or greater. And that is this interval. So pretty cool, right? We did algebraically what we also could find graphically, and they both support each other. All right. Moving on to the next one. Oh, marker board. So if we were in class, we would have done this one. And if you want, you can go ahead and look at that and do it. And you can look at the graph and check yourself. But I am not going to do this because we want to keep this as short and sweet as possible. All right, this is example 2. So here we go. We're going to do the same. We're going to do the same thing. We're going to say, look, inequalities, they're a bit messy, right? So we're going to go ahead and pick an orange, and we are going to make it into an equation. We're going to set it equal to 0 so we have some place to start. Makes sense, right? And so let's go ahead and factor out, how about a 6x squared? Does that sound good? You know what? Yes, while I'm looking at the orange and picking it out, I'm not paying attention to what I'm writing, am I? So 4x cubed minus 6x squared is equal to 0. So we're going to go ahead and factor out a 2x squared. Now, I wonder if you didn't see that, you just factor out an x squared, you're still going to get the same answer. So don't worry about that. But I'm going to go ahead and factor out a 2x squared, which leaves me with 2x minus 3. So I have something times something equals 0. So I know either 2x squared equals 0 or 2x minus 3 equals 0. And so when I solve for this, I get x squared equals 0, which of course means that x is equal to 0. And over here, I get that x is equal to 3/2. So here's the deal. These are two of my solutions if I had an equal to sign here, but I don't. So you're like, Miss Overby, why did you waste all this time to get something that's not a solution? Well, good question. But I'll tell you what. They are very important values because I'm going to include them on my number line. 0 may not be a solution, but it sure is a placeholder, right? And we know how important placeholders are. Same thing with 3/2. It's not a solution, but it's a placeholder. So once we have our placeholders here, we don't care that they're a solution or not. We know that we're going to test to the left and right of them, and we're going to see who belongs and who doesn't. So when we're testing, I want to make sure that you get what we're doing. When we're testing, we're saying we're going to test numbers to the left of 0. Like, for instance, we're going to probably use -1. I'm just looking at what I use, so -1. And that means we're going to plug in -1 to this and compare it to 0. If it's less than 0, we're like, yes, you're part of our solution. And if it's not, then we're going to say no. Checking to make sure this is still going. That's always my fear, right? I make it through 20 minutes and it's gone. All right, here we go. Or it never was videotaped. All right. You know, this is not the time for me to tell you my fears, but that is one of them. All right, here we go. I'm going to go ahead and plug -1 into that equation, and I'm going to go ahead and get -10. Is -10 less than 0? Yes. So welcome to the solution. So we're going to make it clear, while x equals 0 is not part of the solution, it's a nice placeholder because everything less than 0 is part of our solution. All right, we're going to check the values between 0 and 3/2, and all we have to choose is one number and test it. So a good number between 0 and 3/2 is 1. When I plug 1 in, I'm going to get -2. Is -2 less than 0? Why, yes, it is. Congratulations. Welcome to the solution. All right, now, we know that 3/2 is not part of the solution, but let's check to the right of 3/2. Let's use 2 since 3/2 is 1.5. We're going to use 2. We're going to plug it into the equation. And when I did, I got 8. Is 8 less than 0? No. You are not part of our solution. We're going to exclude you. All right, let's go ahead and pick a different color and put it all together. Probably that magenta looks good. So we want to describe this solution, and we want to do it in interval notation. So the first thing I'm going to notice is from here to here. Let's look at that first, because I know that squiggly line has an arrow that means that it's going all the way to -infinity. We're going to include any value from -infinity, and then all of a sudden we're going to kind of come to a screeching halt at 0. Now, do we include 0? I think not. There is an open circle there, so we're going to use parentheses. So x could be either part of this interval, or we're going to include the interval from 0 to 3/2, right? So that interval starts with 0, 0 is not included, and it goes all the way to 3/2. Do we include 3/2 in our interval? Absolutely not, but it's a wonderful placeholder, and we're very appreciative of it for that reason. All right, so let's do the big reveal. Let's see if what we discovered was true. So what we found out was this graph, if we were to graph 4x cubed minus 6x squared, it would be less than 0 over these intervals. Let's see if that's true. All right, so we see where the graph is equal to 0, right? So right here. So where's the graph less than 0? Well, here to here, right? These are all values that are less than 0. And they correspond with when x is 0, that way, -3 to 0. We can see when x is 0, y is exactly at 0, so that's why 0 doesn't count. And then our second thing is that we can also see that from here, all this part, okay, when x is from 0 to 1.5, which is 3/2, it's also less than 0. And so the rest of the graph, the remaining part of the graph, right, doesn't count. So the values that are greater than 3/2 for x produce a graph that's taller than 0. So remember, y is always telling us how tall or how tall and short's not a really good thing, because what are negative numbers? Super short. So, but it's telling us the height of our graph, how high up it goes or how low it goes. All right, so this is our next one, number 3. So now, the first two were just polynomials, right? So polynomial inequalities. And now this is going to be a rational inequality. And so we're going to go ahead and do the same thing that we were doing before, where we, let's pick that purple, where we say, you know what, inequalities are such a mess. Let's just go ahead and start with an equation. And so we're going to, you could choose to cross multiply, or you could choose to get rid of the x minus 1 in the denominator by multiplying both sides. I'm going to do that. Choop, choop, it's gone. And I'm going to go ahead and distribute that -2. So we get the -2x, and we get a +2. And then I'm going to go ahead and add the 2x to both sides and subtract the 3. And finally divide by 3. Let me double check with my work, because when I'm talking and writing, sometimes it can be very dangerous. All right, got the same thing. And now you're like, uh-oh, we only have 1 point on our number line to work with. Actually, that would be a good thing, right? But this is something new. So we're always looking for places where x is equal to, like, see what we solved? We have one solution, right? X is actually equal to, when x is equal to -1/3, that means this whole thing is equal to -2. That's what our work just showed. So we can go to our number line and we can find -1/3, or we're just going to make that -1/3, and we're like, congratulations, you're included in the solution. But the number line also represents what x cannot be. So before, leading up to this problem, we'd find it like we did example 2. You know, there wasn't an equal sign underneath, so those were excluded. But here, when we're dealing with rational functions, and let's use red, we've got an issue in our denominator when x is equal to what? That's right. When x is equal to 1, we have an issue. X equals 1 makes the whole rational fraction, or the rational number, undefined. So can x be equal to 1? No. So we're going to include that in our number line. Let me switch back to the pretty color. So we're going to include that in our number line, but it's going to be an open circle. So that's really important to remember. So that's new. When we have a rational function, we're going to do the same thing as we've always done, but then we're going to stop and look at the denominator to say, wait a minute, what number should I include in my number line where x cannot be? All right, and then we're just, you know, same old game, right? We're going to go ahead and test. To save time, I went ahead and did my testing ahead of time. Hopefully I did this correctly. To the left of -1/3, I put -1. When I plugged it into the left side of the inequality, I got -1. Is -1 greater than or equal to -2? Yes, it is. And if you kind of get confused with that, the negative numbers, just think about a number line. -1 is to the right of -2, so it is larger. All right, let's test in between -1/3 and 0. Let's test the best number in the world to test, and that's 0. If I plug 0 into the left side of the inequality, I got -3. Is -3 greater than or equal to -2? I think not. No, you're not included. We are excluding you from our solution. All right, we are going to go ahead and test to the right of 1. And so we'll test 2. When I plug 2 into the equation, I get what, a 5 on the top and a 1 on the bottom. Is 5 greater than or equal to -2? Why, yes, it is. Welcome to our solution. So once again, we've set the inequality, the left side of the inequality, equal to the right side. We've solved to find some numbers for our number line. And this time, we also set the denominator equal to 0. That's basically what we did to find what x cannot be. And then we're just testing intervals. And so now we're going to go to looking at the intervals we created in our number line and writing them as solutions. So this part, if I wrote an interval notation, would be from -infinity all the way to -1/3. Is -1/3 included? You betcha. So we're going to use brackets, and then this part, now x can be either in this interval or x can be in this interval from 1, and 1's got an open circle for obvious reasons. We cannot include it, and it goes to infinity. So let's see if we're right. So what we have behind this screen is, going on Desmos and putting, let's see if we can kind of, we graphed x plus 3 divided by x minus 1. And when we did that, this is what the graph looked like. And we're interested in knowing when is x plus 3 over x minus 1 greater than or equal to -2? When is the height above or equal to -2? So let's find -2. That kind of looks like -2 right here. Let's see. I'm going to cheat a little bit. All right, so -2 looks like right here. All right, so we're looking for when is the graph this height or below, right? Oh, no, this height or above. So we're looking for any time the graph is this height or above. So when does that happen? It says from -infinity to -1/3. Does that make sense? Let's see, -1/3 would be about right here. So does that make sense from here to here, when x is from -infinity all the way to -1/3, the height of the graph is above -1. I'm sorry, is that what it is? -2. Yes, it is. And it's also from 1, let's see, I think this is 1 right here. From 1 on, it's also above. All right, and you can see that we have a vertical asymptote, and we are so bright because we already know about vertical asymptotes. We know we have a vertical asymptote right there. Kind of curvy vertical asymptote, but there we have it. So our solution makes sense. And on the test, the reason why I'm showing you these graphs, because it's really good to match up something graphical to what we just did algebraically. It really puts the picture together. But also, on the test, it's going to be important that you show me that you understand what you're getting when you solve these inequalities, that you understand you're really looking at a certain part of the graph. So if that's confusing to you, make sure you ask questions in class. If you want to do this, that's fine. You can take a picture of what the graph looks like so that you can check yourself when you're done. We are going to make this video be a little shorter though, and we are going to go to example 4. Once again, we have a rational, and so we're going to be on the lookout not only for numbers when we set this equal to 0, but for numbers that will cause us issues in the denominator. All right, here we go. Let's go ahead and start with that. I'm just like working here. I think my writing looks better. I almost just stepped on my mic. All right, here we go. We're going to set this whole fraction equal to 0, but we already know that really when we talk about a fraction, it's really the numerator that we're looking at to set equal to 0. We will tend to the denominator in just a bit, but we know that when we are looking to make a fraction equal to 0, it's really saying, hey, when is the numerator equal to 0? And so we're going to go ahead and factor that. we're going to go ahead and use x minus 4 and x plus 2. And we're going to see that I'm going to go ahead and not skip a step. You can skip this step, of course. So we're going to see at x equals 4 and x equals negative 2 that makes the fraction equal to 0. Now, do we see an equal here? No, we just see a greater than. So already we know, all right, we got some important numbers here. They're not included, but they are important placeholders. We've got negative 2, and we've got 4 over here. All right, they're placeholders. Now, we're going to look at the denominator because the denominator has some important placeholders for us as well, because we know the denominator cannot equal 0 or the function will be undefined, right? So we're going to go ahead and take that denominator and set it equal to 0. And we're going to remember that we can factor and set each of our factors equal to 0. So something times something equals 0. So we have two important placeholder numbers. They're not part of our solution, but they're important because x cannot be equal to them. What do you think when we peek after we're done behind the screen and we see the graph? Where do you think our vertical asymptotes are going to be, right? So they're important, and we're going to place them on our number line. We've got 0, we've got 3, and now we're going to do a heck of a lot of testing, aren't we? So I went ahead and did the testing. When I plug in numbers to something like this, I didn't want to waste our time by going, let me see, do I have that right? So I went ahead and plugged it in ahead of time. And here we go. If you want to pause this and do this on your own so you can check it and feel like you've got it down a little bit better, I'm fine with that. So go ahead and pause it. But here I go. All right. So I went ahead. I'm going to check. I'm going to use negative 3 to check whether this is part of our solution, because negative 3 is to the left of negative 2. And I got 0.389 when I used my calculator. That is greater than 0. So yay. Welcome to the solution. That's part of the solution. We already know that at negative 2, that's a placeholder. So once again, I'm plugging in the numbers I'm testing into this side, and if they are greater than 0, whatever number I get when I plug that in, then it's part of the solution. So a good number between negative 2 and 0 would be negative 1. When I used my calculator and plugged it in, I got negative 1.25 on the left. Is negative 1.25 greater than 0? No, I think not. You are not part of our solution. Sorry about that. Better luck next time, right? All right, what's a good number between 0 and 3? 1 is always a great number. Let's use 1. I'm going to plug 1 into the left side of the equation. I get 4.5. Is 4.5 greater than 0? Why, yes, it is. Welcome to our solution. So you're part of the solution as well. All right, between 3 and 4, gosh darn it, the only good number between there, are there any good numbers between 3 and 4? I don't know, I'm using 3.5. When I plug that into my calculator on the left side, I got negative 1.571. Is that greater than 0? No, you are not part of our solution. And finally, I plugged 5 in because 5 is to the left as I test to the right. As I test to the right of 4, I'm plugging 5 in, and I got a 0.7. Is 0.7 greater than 0? Yes, it is. Welcome to the solution. And putting this all together, I'm probably going to need a different color because that was hard to see, wasn't it? All right, let's go with orange, and let's put this together. I'm going to go ahead and do this part first. So I've got negative infinity all the way to negative 2, not including. X could be in this interval, or it could be in the interval between 0 and 3, but not including those. That's supposed to be just a 0. Not sure what's going on there. Or it can be in the interval from 4, not including 4, all the way to infinity, and that's our answer. So what I want you to do is look at what you wrote on your sheet, and I want you to compare it, because I don't know if I can see both at the same time. And I believe that if we were to look at this graph and see where it is greater than 0, it is greater than 0 in a couple different places, right? Here, here, and here. And do our intervals describe those x's? Because we're looking at the x's, and I believe it does, right? Here's our negative 2, so from negative 2 on that way. The graph is taller than 0. And also from our interval from 0 all the way to 3, it looks like, because we have a vertical asymptote at 3, right? If we were to put them in vertical asymptote there and there. So from 3 not counting 3, or I'm sorry, from 0 to 3 not counting 0 or 3, the graph is also taller than 0. And then, of course, from our final one from 4 all the way to infinity, the graph is also taller than 0. All right, that was fun. I enjoyed that. Thanks for joining me. I know that you've got some homework, so make sure that you practice, 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 and when I see you in class, ask me questions. All right, thanks.